right, now we can go. So the question on the board says star X127 has the elements hydrogen, calcium, sodium, and helium in it. And then I'm asking you to tell me what the surface temperature of the star is. Well, that sounds kind of unfair, Mrs. McGrain. How am I supposed to memorize all these stars in the universe, Miss McGrain? Am I really asking you to memorize a whole bunch of things, Manuela, am I? No, but I'm asking you to be able to use a classification system. Did I give you a classification system? I sure did. Now, if you will please look, what she has in front of her is this. This is the Harvard classification system, developed in part by Annie Jump Cannon. Do you think maybe you're going to have to do this on the exam? Yeah, you are. So let's practice. I will never ask you to do something that I have not given you the tools to be successful in. I'm going to be quiet for about a minute. It's really hard for me to do that, so I've got a timer to help me be quiet. Because I need visuals. Oh, there I go. Okay, my minute is done. That was really hard for me. Manuela, would you like to help us out with this? Star X127. That's a made-up star, by the way. There's not really a star like that. I totally just made that up. I don't want you to be looking for star X127. Has the elements hydrogen, calcium, sodium, and helium in it. With that information, Manuela, what would the surface temperature of the star be?
6,000 to 7,500.
She's saying 6,000 to 7,500. What's, sweeties?
Kelvin.
Kelvin, good job. Yep, because the unit label matters. So see, she's saying a range of 6,000 to 7,000 degrees Kelvin. Can I have confirmation of that, please? Can somebody else corroborate that? Charlie's saying yes. Landis, yes. All right. So good job. So can I ask, where did you find that information?
The chart. Packet.
Okay, the chart in the packet, right here, where it's got the little picture of Annie Jump Cannon. And this is the Harvard classification system that she helped to develop. Yes?
Why do we use Kelvin instead of degrees?
Good job. I don't know why somebody has said, hey, let's go ahead and use Kelvin rather than let's go ahead and use Celsius. I am not sure the answer to that question. I just know that we do.
Like, do you know how many degrees are in Kelvin?
I don't. I do because I gave that to you last week on the notes. I said that, so his question is how many degrees so if we look at 294 degrees Kelvin, that is the same as 21 degrees Celsius, which is the same as 70 degrees Fahrenheit. Now, if you're asking me to, I don't know how to do that. I would assume we could set up a proportion, like 294 over, I don't know how to do that. Math is something that I struggle with. If I wanted to set up a proportion to figure out how many degrees Fahrenheit this is, how would I do that? Would it be this? Would it be 70, and then this would equal X, and I know that it is 6,000 degrees Kelvin? Doesn't it have to match? This equals, I don't know how to do that.
It's like 10,000 something.
Is it?
Yeah, I looked it up.
Oh, did you look it up?
Yeah, I did.
There you go. I know that you'd have to do a proportion. As far as how to set up the math correctly, Mrs. McGrange struggles with that, and so that's, yeah. I have what's called math anxiety. Does anybody else have math anxiety? No, Ms. McGrange, just you. Well, anyway, I struggle with it, so I could figure it out, but right here in front of you like this, I have no idea, man. I just know those are the equals. All right, good questions. You will have to do some classification. I will not ask you to do any calculations like that, but you will have to do some classification. So when you are using your exam, please make sure this is one document that you want to go ahead and have out, because it's open note. And so you'll be able to use this for your benefit. All right, let's go ahead then and move on. Does anybody have any questions about that? Let's go ahead and move on to the piece of paper that I put in front of you, and it is all about exploring the HR diagram. So everybody should have a piece of paper that has been placed on your desk. Would anybody like to read the introduction for that piece of paper that has been placed on your desk? Honey, thank you so much for volunteering. Go ahead.
The Hertzsprung-Russell diagram is an important tool used by astronomers to study stars. Each dot on the HR diagram represents a star. From this diagram, we can tell the properties of a star, not where it is in the sky.
Right, not where it's located in the sky. So this is not a location device of our night sky. This is a classification system based on how bright is the star, what color is the star, what temperature is the star. And we can fill that in then and say, oh, this little star goes right there, right, depending on those things. So this is going to be a classification tool. This should be the second time you saw this because we showed you this last week when we took notes on stars. So let's go ahead and work through the first one. Number one, our sun has a luminosity rating of 1 because the luminosity scale was based on our sun. We're done with the computer, so you can save your batteries. We'll be able to use the computers later because we're going to do an exit card on the computer to see how we're doing with HR diagrams. But for right now, save the battery. So the luminosity rating was developed with our sun. Anything dimmer than that is below. Anything brighter than our sun goes above. It is a G-type main sequence star. So circle the letter on the chart that represents our sun. Based on those things, what do we think? Where is our sun? If it is a main sequence G-type star, and it's got a luminosity of 1, which letter would be our star? I see one person with their hand up in the air. 2 people, kind of. 3. One of these. 4, 5. Kendi, I'm totally going to you. You got this. So the first thing we're doing is looking for luminosity. It is right here, and you're looking for 1. Right? Now, I'm telling you what kind of a star is it?
It's A. Oh, G.
G-type star. So where are the letters?
Up there.
At the bottom. So if it's a G-type star and it's a 1, you told me just it is what?
A.
It's A. So it is A. That is the location of our sun. So please circle that. Good job, Kendi. All right. What information can we learn about a star by looking at the Hertzsprung-Russell diagram? Use your star notes for extra help if needed. I'm going to be quiet, and I'm going to allow you to write down some ideas, and then we will put some ideas up on the board. What can we learn about a star by looking at this diagram? Oh, I guess I'm daydreaming now. Maybe I should put that by the exam. Today's kind of all about reviewing. All right, we're out of time. I need some hands up in the air. What's one thing that we can learn about a star based on this diagram? Charlie in the back, give me one thing.
Its temperature.
Nice! I can learn its temperature. Oh, come on, little pen. I can learn about its temperature. Nice. I can learn about the temperature. What would be the temperature of the sun from this, Charlie? If we know the sun is located A, that's what Kendi said, and she's correct. What's about the temperature, Charlie, of the sun?
Like 5,000 to 6,000.
Yeah, about 5,000. It's not quite 6,000. It's not, yeah, I don't really know what this, we'd have to figure out what this is. But I think it's about 5,500 degrees. Less than 6, more than 3. What else can we learn about it? Jaden, what else can we learn?
The luminosity.
Nice, we can learn the luminosity. Now, what is the luminosity? What does that mean, luminosity?
How bright the star is.
Right, it's brightness determined on how much energy output there is. Write that down, please. How much energy output. And that does determine how bright it looks in the sky. How much energy output. What else can we learn? Yeah.
The color.
Nice. We can learn the color of the star. Definitely. We can learn the color of the star by looking at the spectral class helps us with that. The spectral class down in this particular area right here can tell us the different colors. Spectral, remember, is that spectrum, it's like a range of energies. And we learned a lot about that last week when we did emission spectra, when we lit chemicals on fire, and then the absorption spectra. Nice job. What else can we learn? Maybe, Manuela, what do you think? You can figure out, I would say that you can figure out the size if you really know how to read this thing and you know where different size stars are located, absolutely how they classify and where they end up. I would say, yeah, the size of the star. Yeah, if you can remember where they go. For example, Manuela, up here where we say, what kind of stars are up here?
The giant ones.
Almost. These are giants. These are super giants. You wouldn't think it made a difference, but it does. I like it. Anything else? Fantastic. Let's go ahead and move down. It says number 3, white dwarfs are located in section D on the diagram above. These are the highest energy stars. What is their general range of temperature? So I am looking for a range of temperatures. You're not just giving me a temperature. So we said the white dwarfs are located in this area. So if you kind of look at this general area and you say, all right, then we need to have a range of temperatures. So if we go from about here to about here, that is what we are looking for. What is the range? And when you say range, you always go low range to high range when you list them. So if someone in science is saying, hey, what's the range of temperatures? Landis, what could we say for a range of temperatures for white dwarfs?
Probably about 27,000 to 7,000.
Good, but we go low to high, man.
Probably 7,000 or 8,000.
Yeah, maybe about 7,000 degrees to about, what, 25,000 degrees? 25,000 degrees Kelvin. Make sure that you're always showing the little degree symbol and that you are always putting the unit label. Unit labels matter Because if you don't put the unit labels, I am not going to understand. Is it Fahrenheit? Is it Celsius? It makes a difference. It'd be like if you were trying to make a chocolate chip cookie recipe, and I'm like, here's my chocolate chip cookie recipe. You need 3 eggs, you need 2.5 flour, you need 1 sugar, you need 3 baking soda. Go to it. And you're like, well, 3 what baking soda? Right? 3 cups of baking soda? Ew. Unit labels matter. Red giants are located in section B. Let's go ahead and see where those are. Oops. Section B is right up here, our red giants. I'll go ahead and write that for you. Big red giants. So if that's where they are, I'm asking you compare their temperatures to the white dwarfs. So when we are comparing in science, you're doing things like red giants are hotter than white dwarfs. Red giants are cooler than white dwarfs. So Amy Hernandez, if we're comparing our white dwarfs, which are here, to our red giants, which are here, what comparison words would you be using?
Red giants are cooler than white dwarfs.
Nice! Red giants are cooler than white dwarfs. Look at you. Red giants are cooler than white dwarfs. We are practicing writing like scientists. Period. Delaney, this one's for you. Supergiants are located at section C. So I'm just going to go ahead and label these supergiants. Supergiants. Supergiants are located at C. What is their general they are much more massive than red giants. What's their general luminosity? About. 10 to the fourth? 10 to the fourth? Okay. So they're about 10 to the fourth power. So we're going to go ahead and write it like this. 1 times 10 to the fourth. Now, sometimes you will see it written such as this. You will see 10, and you'll see a little caret that goes up, and then you'll see a 4 like this. That also means 10 raised to the fourth power. Okay? You're going to see that in an exit card I'm going to give you at the end of class today. So I want us to compare. Is this dimmer or brighter than our sun? Jesse, what do you think? Is 10 to the fourth power dimmer or brighter than our sun?
I'd say it's much brighter.
It is much brighter than our sun. Because our sun has a luminosity rating of 1. So these are much brighter. All right. Let's go ahead and look at number 6. Luminosity is the total amount of energy emitted, meaning put out per unit of time by a star. How is it possible that red giants have a higher luminosity than white dwarfs, even though red giants have a lower temperature? What? That's crazy. Let's go ahead and look. Our red giants are located here. They have a temperature of around, I don't know, like around 4,000 degrees. Those would be like our red giants, between 3,000 and 4,000 degrees, or 5,000 degrees. Our white dwarfs are super hot. They have a range of about 7,000 to 25,000 degrees. So if these are so much hotter in temperature, how can these be so much more luminous? Because if we look at the white dwarfs, they're very dim, and the red giants are very bright. They're putting out a lot of energy. Why? Jaden, what do you think?
The red giants have a larger mass, which means they have to put out more energy
They do. They have a much larger mass, but they could also have, these could have a larger mass as far as like being very dense. They could be very small in volume, but very massive in how much atoms they have because they're very dense.
How big they are.
How big they are? You mean like surface area?
Yeah, surface area.
Yeah, surface area. So our red giants have a much larger surface area. So red, oops, that's not how you spell red. Wrong red. Red giant stars have a much larger surface area. So they are putting out more, I'm going to say energy, I'm just going to circle with that E, that old symbol I used to use, more energy per, I guess, I don't know, per unit. I'll just say per star. They're putting out more energy per star because they're just so massive. They have such a bigger surface area. It'd be like my husband. He's 6'4", 6'5". I'm not. I'm like 5'3". He has a much larger surface area than I do. So, like, as far as heat that he's putting out so much heat as a human being because he's just got so much more skin everywhere that he's just putting off more heat everywhere. Even though maybe I would have a higher temperature than him if I was sick, if you put him and I under like an infrared camera, I mean, he's just going to be putting off so much energy because there's just so much more of him. Are we finished, or is there one more here? What? Think about the electromagnetic spectrum. If red stars are the lowest temperature stars, what do you think the temperatures of the blue stars would be in comparison? Remember our electromagnetic spectrum. If we had red down here and we had blue up over here, and we had our short wavelengths, oops, wrong, Miss McGrain. We had our long wavelengths of red, and then it got shorter and 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 shorter. So we have low energy down here, and we have high energy down here. If red stars are low in temperature, I'm going to say low E, and this is low temperature. This would be high E, which would mean what as far as temperature? Charlie?
The blue stars would be hotter.
Yeah, they're going to be burning much hotter. These are going to be higher temperatures. Higher temperatures. Much higher temperatures. Those would be like your blue stars on the main sequence. Those would be like your blue giant stars. White stars also are pretty hot. Red, orange, yellow, those are pretty low energy stars. Now I know that where we grew up, you know, things like frozen, you know, blue, that's cold. Even on our hot and cold on the water taps, right? Hot means red. Well, in astronomy, it's different. Red means cooler stars, blue means hotter stars. You have to kind of switch your mindset. I want to show you a little video that I wanted to show it to you before, but I think that it's going to be much better now. So I'm going to go to Canvas. This will give you an opportunity to see it. It is our little introduction video right here, and it is using,
This is a Hubble Space Telescope image.
it is going to be utilizing the HR diagram as far as classification.
Hubble Space Telescope image of the crowded core of the globular cluster Omega Centauri. The brilliant colors of the stars are real. They correspond to stellar temperatures. They can also be used to trace stellar evolution. Astronomers like to know how blue the blue stars are and how red the red stars are. So we'll first sort these stars out by color. blue on the left, and red on the right. Next, we'll sort the stars according to brightness. The brightest stars at the top and the faint stars at the bottom. The final plot you see represents different stages of evolution of stars. Stars spend most of their lifetime burning on the main sequence. When their fuel starts to run out, they expand to become red giants. They find a new source of fuel, helium, and burn blue hot, but even that runs out. They end up burning out as white dwarfs. Based on images for the Hubble Space Telescope, we've assembled a true plot that is a snapshot of the life history of stars in this ancient cluster.
So that's kind of how they figured out the HR diagram, okay? They said, first let's categorize them by colors. We've got red, orange, yellow, white, and then we've got our blue. And then we're going to say, okay, the dimmest ones go down here, the brightest ones go up there, and so on. Just kind of seeing it in action, that's all. Not that exciting. All right, the next thing that I want to do is I want to practice using the HR diagram. And so we are going to do that together using this large HR diagram. And I want to give each and every one of you a large HR diagram that you can use in your notebooks, and you can use this also on the exam. So this is going to be for you, and on the back, we've got some stars. Oops, sorry, that's upside down. We've got some stars, and we're going to try to see if we can figure out where these stars go on the HR diagram. So I have hole punched these for you. You're very, very welcome. Back in the day, I used to have everybody kind of come up and write the letter where they thought it goes. I guess we can still do that. I'll just have to sanitize the marker each and every time that we utilize it. Or I guess I could just give a new marker each time. What kinds of things I'm thinking about. So check out your little diagram. I am going to try to find some markers that we can utilize. And then I can sanitize all of my markers. Okay, so you've got the HR diagram. On the bottom, we can see temperature, and on the side, we can see luminosity. And then I've got them also by colors for you. Blue giant, the main sequence runs all the way through the middle. White dwarfs, red giants, and then red supergiants. Good? Fabulous. So if you look please at the back, I would love for this to be able to fit all on one side. There's got to be a way that I can fit these all on one. This. How do I do this? No, I don't know what that is. That's done. I don't want that. That's not good. I didn't get rid of that. No, I don't want that either. I just want to see the whole thing on one screen. And apparently, I can't do that. Let me try this. There we go. Fabulous. There it is, all on one screen. So if we look at the back side of our sheet of paper, it says, all right, we're going to put these letters where we think approximately the stars go. The first one says star A is approximately 40,000 degrees Kelvin, and it is in the main sequence stage. So then what you would do is you would take your pencil and you would put A where you feel it is. So it's not these letters down here, A. It's just kind of like, hey, where do we think it could possibly be? Good? Yes? No? Great. So I'm going to give you some time to do that. I will put about 5 minutes up on the clock, and then we can come and see how we did as far as where they go on the HR diagram. if you're not sure, skip it. And just circle it if you're not sure. The temperature here is a little bit easier to figure out because this is, 2,500 is half of this. It kind of goes up. Just kind of try to divide them a little bit as best you can. Oh, goodness. Thank you. I'm gonna give you some hand sanitizer, not because I think you're yucky. Nothing to say. And my timer didn't go off. I don't know why, but it should have gone do-do-do-do-do-do, do-do-do-do-do-do-do. So do-do-do-do-do-do-do, and we're done. let's go ahead and check to see where we are at. Who wants to do A? Letter A. Potentially, where do we think maybe, okay, yeah, Colton, could you tell me about where do you think letter A should be? It says approximately 40,000 degrees Kelvin, and it's in the main sequence. So if it's in the main sequence and it's about 40,000 degrees, where do you think generally it should be?
Farthest one.
The farthest one. What color do you want me to put down here? Where are we looking at?
Blue.
The blue. So this one would be about 40,000 degrees, and I would agree with you. I would say that that would probably be the A, letter A. I would say that would be letter A right there. Anybody else disagree, agree, we good? Okay, fantastic. Let's go ahead then and look at B. It says it has a luminosity of 10 to the second, or 10 raised up to the 2, and it's got an approximate temperature of 5,500 degrees Kelvin. Delaney, this one's for you. Where do you think it should generally be? Or how about what color first, so that I can dial myself in?
It's yellow.
Okay, she's saying that it is yellow, about 5,500 degrees, and it's got a luminosity. Oh, okay, so like up in this area? She's saying it should be somewhere up here. Can I see thumbs up or thumbs down for that? We have thumbs up, okay. Enyo, why don't you do letter C? It's very old, it's about 30,000 degrees Kelvin, and it's not very luminous.
I put it like in the white doors, but like to the left.
In the white dwarfs, but to the left, so between 20,000 and 40,000, not very luminous, so it could be something you're saying down in this general area?
Yeah.
Right there. Agree or disagree? I would agree. Okay. Landis, letter D. It's around 3,500 degrees Kelvin. It's still fusing hydrogen in its core. Do you remember the stars that are still fusing hydrogen? Where are they located?
In the main sequence.
In the main sequence, that's right. So if we know it's in the main sequence, because it's still fusing hydrogen in its core, and I've given you a temperature of about 3,500 degrees, where do you think it should be?
In the bottom right,
Bottom right? What color you want it to be?
red.
About red. So are you looking like in this general area or this general area?
Oh, the first one.
The first one. All right, so you want me to put a letter D somewhere around here? Would we like that? Yes or no? Pretty good? Fabulous. Kendi, do you feel comfortable doing E? You didn't do that one? Okay, Manuela, what about you? E? It's about 3,500 degrees Kelvin. It's very massive, and it's fused elements past helium. So we know it is no longer on the main sequence. If it's not doing hydrogen and helium, we know it's not on the main sequence. So where do you think, Manuela? First of all, what color do you want me to, what do you want me to be?
Red.
Okay, so she's saying red. So somewhere between here and here, we know it's not here, so it would have to be maybe this one? Higher up? This one? You think it's higher up? It could be this, or it could be this. Either one of those is going to be perfectly acceptable, okay? But we just know it's not on the main sequence anymore. So it could be maybe potentially here, or, oops, here, or it could be here. Did you say E up here because I said it's very massive?
Yeah.
Yeah, absolutely, it could be there. So I'll go ahead and get rid of that one then. That's what you went with. All right. Well, the free space is just, I think that at one time we used to play, or somebody played a game with this. I never did. G, a very massive star. It's still fusing hydrogen, and it is very hot. So, Hani, this one is for you. If we know it's still fusing hydrogen, that means it has to be where?
Wasn't it, white dwarf?
It's not going to be a white dwarf if it's still hydrogen. Paris, you want to help him out? Yes or no? No. Okay. Jaden, help him out. If it's still fusing hydrogen, where is it going to be located? If it's still fusing hydrogen, it's going to be on the main sequence somewhere. So, honey, it's going to be somewhere here if it's still fusing hydrogen. So then, based on that knowledge and the fact that it is, which one am I doing? G? If it's a very massive star, but it's still fusing hydrogen and it is very hot, what could it potentially be?
Blue giant.
Yeah, it could be, well, not a blue giant because it's still here. It could be anywhere in this general area because it's still on the main sequence. And these blue giants are not on the main sequence anymore. It could still just be somewhere in here. Our sun. We've talked about that one so much. Our sun is around 6,000 degrees Kelvin. It is a luminosity of 1, so I'm going to say that potentially this could be our sun. Somewhere here. That's our sun. Kendi, do you feel comfortable with I? It's got 15,000 degrees Kelvin, and it has a luminosity of 10 to the negative 3. So 15,000 degrees, 10 to the negative 3. What do you think?
Like where the red is?
Where the red is? Here? Okay, so 15,000, if this is 10,000 and this is 20,000, 15,000 would be somewhere here, so it would be around here. And if we're looking 10 to the negative 3, this is 10 to the negative 2nd, this is 10 to the negative 4, so 10 to the negative 3 would be somewhere in between here. So if we have this and this meeting up, it would probably be somewhere in the white dwarf area. All right, so I'm going to go ahead and put I somewhere in here. Fabulous. What will we don't know J yet, what our sun will turn into when it no longer fuses hydrogen. Does anybody want to put a guess on that? I think we've talked about it a couple times. Yep.
The farthest one of the red giants.
Yeah, it will turn into a red giant. I don't know if it'll be the furthest one over here because these are just kind of like examples, but it definitely will be turning into a red giant. So our sun eventually, when our sun ages, our older sun, we can put over in this general area. Okay, it's Betelgeuse, or some people say Betelgeuse. It's got a temperature of about 3,200 degrees Kelvin, so it's fairly cooler, and it's got a luminosity of 10 to the 6, so it's very luminous. Amy, which one do you think that is? Or where generally? It's not like a specific one, but generally where would that be? 3,200 degrees Kelvin. And it is got a luminosity of 10 to the 6th. What?
Is it gonna be in the red supergiant?
Yeah, it's going to be up here. It could possibly be this. It's going to be up in that area. Very, very large, very, very bright, but cooler temperature. So it's going to be somewhere in this area. Okay, Sarah, you want to try? Paris, you want to try this next one? Jesse, you want to try this next one? It's L, a relatively cool star. It's got a luminosity of 10 to the negative 2nd.
I did not do that one.
All right, let's go ahead and try it. We know it's relatively cool, so it's going to be down on this end.
Okay.
It's 10 to the negative 2nd, so it's somewhere in this general line right through here.
Probably one of the red-orange ones?
Probably one of the red-orange ones, right? If it's generally cool, it's probably going to be in this general area. I would agree. So I'm going to put L somewhere around here.
2 minutes, Mr. Grimes.
Thanks, appreciate that from you. All right, I have an exit card that I would like us to do so that I can see who's picking up what I'm putting down and who's not. This exit card needs you to get your computer. It is not something that will ever go against you, but I want to know, hey, how are we doing? If you want to go ahead and do it on your phone, do it on your phone. As long as you can get to Canvas, that's absolutely fine. I want to show you where to find this on Canvas. So on Canvas, it says right here, exit card, check for understanding. So if you click on that, you're going to put your last name, your first name, and then I've got a code that I want you to put in order to be able to take this exit. It's a multiple choice. All you're doing is picking one of the situations that I'm giving you. Your code, in order to get into this, is nerf herder. Nerf herder. Like console? Like
Yeah.
nerf herder? Like nerf herder.
Oh, okay. I didn't remember that.
So you're going to type in nerf herder, please. And that will allow you to open up what it is I want you to do. I'm going to show you one more time where that is. It is right here, exit card, check for understanding. Again, not going against you, but when you do it,